Hello, everyone. Happy
Hello.
Monday. How's everybody doing?
Pretty good. How are you doing?
I'm doing well, Daniel. Thank you for asking. Um, Happy to be talking about physics on a Monday afternoon. So there you go. It's exciting stuff we're talking about. Brief recap, you've got a Kappa up that's due Thursday. There'll be one more Kappa next week. Our final exam is next Friday. I think that's about it. Any questions or concerns about where we're at or where we're going? Somebody is calling me. Go away. Okay, then let's pick up where we left off. You might remember we had kind of left at a cliffhanger. Specifically, we were thinking about this situation where you have a laser on a train that bounces back and forth, and somebody on the train measures a specific time that elapses between those two events. And thinking about somebody on the ground witnessing that same event, this is a longer delta x and a different, therefore, and longer delta t, because both of those observers must see this light traveling at exactly the same speed. And we did some math, we did some algebra to determine exactly how much longer must have passed in this frame as opposed to this frame. And we found that it was just our gamma factor from the last, from what we had derived for Lorentz transformation. And we left off thinking about this in the opposite sense. So what if instead of putting the laser on the train, we put the laser on the platform and do the same experiment? So basically the result of the first experiment was that time must be running slower for someone on the train than it is for somebody on the platform, right? But then we turned it around at the end of class last time and said, what must happen for somebody if somebody on the platform did the same experiment? And because the laws of physics have to work reciprocally, meaning everybody has to agree on the laws of physics no matter where they are, if an observer on the platform sees clocks on the train moving slower, it must also be therefore true that someone on the train sees the clocks on the platform moving slower. And the question at the end of the class last time was, how in the world is that possible? How is it possible for both observers to see each other's clocks moving slower? So, any thoughts? It's not an easy question to answer, and it sort of lies at the heart of most of the paradoxes that you run into regarding special relativity. There aren't really any paradoxes at all. That's the first hint. All of these are apparent paradoxes, and the paradoxes are resolved when you can break your mind free of the restrictions which, common sense has imposed upon it over the first 18 to 22 years of your life. No thoughts?
Would it come down to like observing how it's happening? Kind of like if you're in a car driving 60 kilometers an hour toward another car that's coming at 60 kilometers an hour, you both think you're approaching each other at 120. So is it more of reference frame than time is actually changing?
No, it is not. That's a good guess, but that is not exactly what it is. In fact, it's not that at all. It is not. Time really is behaving fundamentally different for these two people, and that is kind of cool. So let's dive into it and see if we can understand it. Before we get into the nitty-gritty, I want to introduce a concept called proper time. And so let's think about this. For any two events, it is always possible to find a reference frame. It is always possible to find a reference frame where either delta x equals 0 or delta t equals 0. That is already an interesting statement, right? Think about that. This is, before we started thinking about special relativity, you would have written this sentence down and thought it had any bearing on reality, right? So I'm talking about an event that occurs here on Earth in 1900, and an event that occurs on, let's say, the star Alpha Centauri in the year 2000, right? It is possible for an observer to think that those either happened in the same place and time, or either in the same place, with delta x equals 0, or to have happened at the same time, delta t equals 0. That's an odd thing to say. Now, can you think of what is the situation for that particular thing? Well, if you have an observer that left Earth in the year 1900 and then traveled straight towards Alpha Centauri and got there in the year 2000, over those 100 years, then that person would say, yes, that first event happened at x equals 0, and yes, that second event happened at x equals 0. That's not the one that's surprising to you. What the surprising one might be that there is always, if that's not possible, in other words, if you can't get from one location to the other unless in any sort of speed of light movement, then it must be true that there's another reference frame at which they happen at the same time. And that's the weird thing. Anyway, we'll think about, we'll ponder this thing more carefully later on. But let's just take it as truth for now. So they happen at the same time or place. So for this example, who is in which observer? So the proper frame is the one in which the proper frame for these two events is the one in which delta x equals 0 or delta t equals 0. So the question is, which of these two scenarios, who is in the proper frame for this event? The person on the train or the person on the platform? And
is the person on the train in the proper frame because the light leaves and returns the floor at the same position?
Right. Let's think about what the two events are. The two events are the laser beam leaving the laser and the laser beam returning to the same location, right? Those two events, I've drawn them a little bit separate here so you can see the down and back, happen at the same position at delta x equals 0 for this person on the train. They do not happen at the same position for the person on the platform, right? Okay. So here is the thing. Time runs fastest in the proper frame. That deserves a box. So if you can identify so this is going to be important when you're solving homework problems, because you're going to be thinking about, there's going to be factors of gamma that show up all the time. You're going to say, person X observes some time difference to be this. What does person Y believe, right? And you know that they're different by a factor of gamma, right? It's usually multiplying or dividing by gamma. You're going to need to know whether you're going to need to multiply or divide by gamma. Figure out who's in the proper frame. That will have the shortest delta t between any two events. Okay. So let's go back to thinking about how we can observe. Two observers can see both see the other time moving slower for the other person. Okay, so let's think about this. The train observer clocks does the train observer need to use to measure this time difference out and back? The answer is just 1. If the time observer has a single clock here, that observer can measure very accurately the time it takes for that light pulse to go out and come back. This person on the ground is not so lucky. This person on the ground actually needs 2 clocks, right? One of those clocks is here, and the other of those clocks is here, right? This person cannot, actually, one person can't even measure this, right? Because this person would need to be both here and here to make that measurement, and that's not possible. So what do we really mean? We mean that 2 people, really, one here and one here, at rest to one another, who have synced their clocks and agree on what time it is, recorded these 2 events, one that happened here and one that happened here, right? And then after the fact, they can go back and compare and say, okay, well, this event happened at this time and this event happened at this time, so we can calculate some delta t and how long it actually it took between these 2 events. That's what it means to time something, right? But it takes these 2 clocks. According to this observer, these 2 clocks agree with one another. According to the person on the train, they do not agree with one another. Let's see if we can visualize this in the Minkowski space. Here is a Minkowski diagram. This is the X and the X frame, CT frame, or plane or axis. Again, this, let's call the unprimed observer the platform observer. We know that this is, here is our C, that's our speed of light line. Here is our X prime frame. Here is our CT prime frame. Where are these? So let's say this is the event of event 1. Event 1 is laser leaving, laser pulse leaving the laser, right? Let's just say both observers agree that that's X equals 0, T equals 0, X prime equals 0, T prime equals 0. Usually that's what you'll do. You have one event, set that equal to 0, and then it makes all your other calculations a lot easier. Where is the second event in this diagram? The second event being the return of the laser pulse to the original position here and to some other position here. Where is that on this Minkowski diagram?
Would it be on the x-axis just a little bit to the right, or some distance to the right?
Like here?
Yeah.
Okay, let's think about what this means. What is different about this point and this point? What is the same, I should say, about this point and this point?
Okay.
At that point, time is still 0.
The time is the same for these 2 points, right? So this is something else we're going to talk about in a minute. This would be a measurement of some length in the unprimed frame, but this can't be this point because some time has passed for both frames. So we have to be somewhere up above the x-axis in this diagram. Good guess, though.
So would it be on the C line?
On the C line, that's a good guess. What would this imply? Let's mark a point here and think about what that point would mean.
That would imply when the laser reaches a height h before it goes back to the origin, or not back to the origin, but bounces back. Going.
Yeah, sort of. This would be again in time. Let's not even worry about the CT prime X prime frame for a second. Let's think about this in the unprimed observer's frame. What would be the scenario at which an object started out at 0 and ended up at here sometime later? how fast would you have to be traveling?
Speed of light,
Right. And what direction would you have to be moving in?
positive x direction.
Yes. Right? This light actually isn't traveling at the speed of light in the x direction. It's traveling the speed of light in that direction, but the x direction, this is only the x component of that, right? So this would be the world line of a beam of light that started off pointing in exactly the x direction and going in that direction. This one won't be moving quite that fast in x, and even worse, turns around and comes back to some point in x eventually.
So would the second time point, would that would be somewhere on the CT primed line, right? Because it returned back to the 0 point in the CT in the
Right.
T prime frame.
That's the clue that we have here. We know at some time later, and this event occurs at x prime equals 0, because it's the same point in the primed observer's frame. This is the locus of all points where x prime equals 0. It has to be somewhere along the CT prime axis. We don't know where, it doesn't really matter. Somewhere along this line. Okay, great. So we can figure out what delta t is, right? Delta t, we just move back to the t parallel to the x prime to the x-axis. That's our delta t. Now let's rotate this whole thing, right? Let's move it. So this is explaining how, it's not clear, but there's actually different delta t's because we've had some stretch scale things. Let's rotate this axis to be now from the perspective of the primed observer. Let's make this the x prime frame, and let's make this the CT prime frame. Where is the CT axis now?
Sorry, is this a rotation or a Lorentz transformation?
Lorentz transformation, but let's not even worry about that yet. Let's just, individual lines move the way we expect them to. It's just that they get stretched and squeezed in between.
Wouldn't it be in the negative x-axis or a negative x prime axis, where CT would be? Be going up to the CT would go up to the left.
Yes, that's right. So from the train's perspective, the observer on the train is at rest, and the observer on the platform is moving backwards at the same speed, right? So it's going to look like that. There's your CT prime frame. Where's the x prime frame? We haven't talked about this. The x frame would be down below, something like that. So that's weird in itself. So this gets weird. It doesn't look like things have scaled, but things have scaled, remember. We have this stretch squeeze rotation. So again, we have to move back to the CT frame parallel to this x frame, and you get these events occurring in different ways. Here's another, I think, nice way to visualize this. It gives me some, let me see if I can pull this up real quick and give you access to it. Okay, here it is. Let's see if I share this with you, if you can see it. Stop share. Okay, are you seeing my Mathematica sheet now?
Yep.
Excellent. So, I've got some representation of Minkowski diagrams, but the cool thing is I can move this event around and it's giving you, so let's just play with this for a minute. I have a slider here where I can move V from -1/2 to 1/2. That's exciting. You can see instead of CT prime, you've got red CT and red X, but it's the same thing. You've got the moving frame and you've got the rest frame, okay? And now the interesting thing is we can move this around, and you're going to get the value of x and x prime and ct and ct prime for any event in this diagram. So let me make this as fast as I can make it, 0.5, and let me move this event up to the point where I know that it could be the laser, right? So in the frame of the train, we've got some event here, which is the laser returning. X equals 0 is and t equals 0 is the laser leaving, and this non-zero point at x prime equals 0 is the laser returning. And you can see that more time has passed between these two events for the unprimed frame than have passed for the primed frame, right? This person standing on the platform sees more time elapsed. This person sees this person's clocks moving slower. But let's turn this around now. What happens if the laser is on the platform? If the laser is on the platform, then what is true about the x position of both of these events? Again, the laser leaves at x equals 0, bounces off some mirror, and then comes back at x equals 0. The x prime coordinates of those two events are different, right? This is that point, right? You can see the x prime position of the original one is 0, but as the train motors by, the x prime location of the second one, where after the lasers come back, the train has already gone way to the right in positive x, and so you're seeing that position, that second event happened at a very negative x prime value, and you can see it's well behind the ct prime axis. Okay, well you can see the observer on the platform measures some time delta for those two events. An observer on the train measures a longer period for those two events, a longer delta t, a larger delta t. So yes, it's true that somebody on the train is seeing the ground's clocks move slower, and it's true that somebody is on the platform sees the train's clocks moving slower also. That's a lot to wrap your brain around, and it's kind of tricky to think about, but here is the bottom line. The ground observer thinks that these two clocks are synchronized. The train observer does not think that these two clocks are synchronized. The train observer sees the second clock being ahead of the first clock. And that's how they can resolve this seeming paradox. They don't agree. They agree that time is equal here. They don't agree on the times of any other locations in this CT diagram. And that's the weird thing. They don't agree, the clocks don't agree at they don't line up at any other location. In fact, they don't even line up at any location, even along the x-axis, right? Because think about this. This is the locality of points where t equals 0. T does not equal 0 anywhere on this line. T prime does not equal 0 anywhere on this line except for this point right here. This point has a negative t prime value. These two observers do not agree. And the opposite is true. This is the location of points where the primed observer thinks that t equals 0 for all points. The non-primed observer sees these as all positive. And these as all negative. They do not agree that those clocks are synchronized. And that's how you can have this apparent paradox resolved, an apparent contradiction resolved. Okay. Let's try to do length contraction real quick. Similar experiment. Let me share my whiteboard again. Okay. Similar experiment. Now we've got some grassy knoll or whatever, and we're going to measure, let's say observer A is moving by on a really fast moving train or rocket or whatever. Observer B lays out 2 stakes on the ground. And observer B measures the distance between those 2 stakes and says, aha, that length is L. Right, we've got some x1 value and some x2 value here. What does observer A see? Well, what are these 2 events of the measurement of L? X1 and X2. Let's draw a little Minkowski diagram up here. I mean, this is weird to think about this as an event, but in order to measure these 2, this distance, this delta x, you have to have this be 2 different events. So if this is x-axis and the CT axis, what are those 2? Well, let's let x1 equal 0. That's always an easy thing to do. Where is the x2 event for B's measurement of the length of that rod?
It's just to the right, still on the x-axis, right?
Exactly. So again, what does it mean? Well, if you've got something here, you need to measure it at the same time, right? It's the length of anything is the instantaneous delta x from one to the other at the same time. Great. So for observer B, right. So what does observer A see? These events do not happen at the same time for observer B, right? Let's use Lorentz to calculate these 2 events. So A, let's say we put them at 0 and some not and some at the origin and some non-origin point. Well, let's be more general. Let's say they're over here. There's x1 and there's x2. It doesn't matter. That's a valid delta x measurement as long as they happen in the same time for the non-primed observer. That satisfies this thing. So let's be more general. x1 prime. So we want to know for the primed observer, meaning A, what is the position? What is x1 prime? What is the position of this location in the prime frame? This is, of course, just well, apply the Lorentz transformation times gamma times x1 minus vt1. And we know that x2 is the same thing, prime. Gamma times x2 minus vt1. Where t1 is just the time at which this event takes place in the unprimed frame. We can also transform to figure out what times these 2 happen at, right? T1 prime equals gamma times T1 times Vx1 over c squared, and T2 prime equals gamma times T2 minus Vx2 squared, x2 over c squared, right? But it's also true, we already said this, that T1 equals T2, right? This is x1 T1 and x2 T2. In this case, since we're measuring this, T1 and T2 are the same. So we can just make this a T1. In general, you'd have a different time here, but these 2 happen to happen at the same time in the unprimed frame, so we can make those 2 the same thing. Okay, so delta x prime. Let's think about what is the delta x going to be for the primed observer. This is going to be x2 prime minus x1 prime. This is going to be gamma times x2 minus vt1 minus gamma times x1 minus vt1. And that's going to be gamma times x2 minus vt1 minus x1 minus vt1 plus vt1. And the vt's actually go away. That's exciting. So this is gamma times x2 minus x1, which is gamma, and x2 minus x1 is just L. Oh, I didn't, there we go, I can see it now. Great, are we done? Well, not quite. Remember, we're gonna calling this length contraction. What's true about gamma?
Always greater than or equal to 1.
It's always greater than or equal to 1. So what's true about delta x prime? It's always greater than or equal to L. Well, that's weird. That seems like it should be a length stretch and not a length contraction, because delta x prime has to be greater than delta x. L is just delta x, x2 minus x1. Well, if you watch the Minute Physics video, if you haven't watched the Minute Physics video, you have to go back and watch it again, because they do a very good job of explaining, getting to this point without the algebra, just by showing you the diagrams and explaining why this isn't really the measurement of the length of between these two poles in the ground as measured by the primed observer. Why not? Why isn't this a good representation of the distance between those two rods in the primed frame?
Isn't
What is true about T prime 1 and T prime 2?
they're different?
They're different, right? That would be like, you know, you're driving by some I don't know, some lake, and you measure the beginning of the lake at one time and the end of the lake at the other time and say you've got a delta x there. No, you have to measure those two at the same time, or it's not a valid distance. It's not the actual length that you would measure for that thing, right? You have to measure it at the same time in order to call that a length. You have to measure the two endpoints at the same time, especially if you're moving by it. If you're moving by it, it looks like the positions of those things are changing all the time. You don't measure the two at the same time. You're measuring some weird other thing besides the length. You have to measure both ends of that thing at the same length. So this is true. Delta x prime is this, but this delta x prime between these two events is not what the primed observer would say is the length of that, or the distance between those two sticks, or the length of whatever object you're talking about. So we need to measure it in the same time. We need to measure these two events in the same time as measured from A. So let's think about that. We know that delta t prime between these two events is delta x prime, is gamma times, I already wrote these formulas down. I'm just going to copy them now. I've already erased them, but let's think about what the delta t prime is. This is gamma times t2 minus vx2 over c squared times, or a minus, this is t2. I'll just bring the gamma out and do this in one step, minus t1 plus vx1 over c squared. And this is equal to gamma times t2 minus t1 minus v over c squared times x2 minus x1. Okay, now, oh, and T2 minus T1 are the same, right? These two go away. That's useful. This is minus gamma times x2 minus x1, which is L, times V over C squared. What does the negative sign mean?
It's a shrink.
Not really. This is a delta t prime. What it means is, so this is the t prime. So this would be x prime to t prime 2, right? And x prime 1, t prime 1, What this means, again, we're just what was this delta t? It was t2 prime minus t1 prime. We just took the difference between those two. It means that the x2 point happened at a negative time relative before the t1, this point. This point happened before this point. And that kind of makes sense if you think about it, because if you put both of these on the x-axis, right? Where's the x prime frame? This point happened at 0. This point must have happened at some negative t value. It's below the x prime frame. Okay, that's what this negative sign means. The absolute position of this is smaller than this one in the prime frame. Okay, we need these L primes though. If we want to get L prime, you need these two events to happen basically at the same time. We need to have them on this axis. So in the time, so what do we need to know? We need to know how far the train moved between this time and this time. And if we know that, we can use that to correct for how the location of the train and how it changed between those two events, and correct our delta x prime measurement to actually get an L prime, the length in the x-axis, or in the primed axis. Again, I need more board space here. I'm going to delete this, but this doesn't really matter. We know the delta x prime equals gamma L. I don't need to work for that anymore. So let's see if this will give me enough space to need what I would do. Okay, so we need L prime to be measured at the same t prime time. In the time delta t prime, how far will the train have moved? In delta t prime, train will have moved a distance v times delta t prime, right? The train is moving at a velocity v. Both observers agree on that. In time delta t prime, that's how far the train has moved. That will be the coordinate we need to use for L prime. L prime is just delta x prime, the distance between these 2 points in the prime frame, plus however much the train seems to have moved in that time. This will correct for the fact that these aren't happening at the same time, correct for that delta t, correct that length for that delta t. Okay, we know that delta x prime is gamma L. We know that this is negative, are you seeing this? Yes. Gamma L v over c squared. So we can pull a gamma out and an L out, L gamma times 1 minus, oh, I forgot the v here. There's another v here. V squared over c squared. But wait a second, what is 1 minus v squared over c squared?
That's 1 over gamma.
It's actually 1 over gamma squared. 1 over gamma is 1 over the square root of 1 minus v squared over c squared. So this is 1 over gamma squared. This is L gamma over gamma squared. Guess what? L over gamma. L prime. This is the crazy and beautiful symmetric thing about this whole thing. Yes, the primed observer sees this delta x as being larger, but in the reference frame of the moving observer, where you're going to measure things at the same time, the apparent distance between these two posts, as measured at the same time from the moving observer, becomes smaller by a factor of gamma instead of larger by a factor of gamma. And that's, again, if you want a better visualization, look at the Minute Physics video. They do a fantastic job of showing you graphically why this has to be true. So this is length contraction. In the frame where you're measuring things at the same time in the prime frame, that distance will appear shorter. So we'll will therefore observer B see all of A's rods appear shorter or longer? Again, physics has to work reciprocally. So whatever A sees for B's rods, B must see for A's rods. A will see all of the lengths in B's frame in the X direction contracted. B will see all of the lengths in A's frames contracted by exactly the same amount, this gamma factor. Okay, one other note, this effect is only in the direction of motion. It does not affect the Y or the Z axis in any way. Length contraction does not affect the Y or the Z. It only affects the directions, the lengths in the direction of motion. So if you have a square, if there's a square in B's reference frame, A will see that not as a square, but as a rectangle. If there's a circle in B's reference frame, a static circle, then A will see that as an ellipse. Everything gets switched only in the direction of motion. Okay, let's do a quick summary of where we've come. The proper frame, this is an important thing. One that travels, I'll say one that travels with the rods or the clocks in question. One that travels with rods or clocks in question. Time runs fastest in the proper frame. All other clocks appear to be moving slower. Others will measure a larger delta T, therefore. Lengths are longest in the proper frame. Lengths are longest in the proper frame. All of the observers measure a smaller delta X. And both scaling factors are gamma.
So in the first problem with just the train and the laser, the person on the train has the proper frame because there is no delta X. But could you also say that it's the proper frame because we're only using one clock in that scenario? So
I'd say those two statements are equivalent.
okay.
The fact that delta X equals 0 means you only need one clock to be able to measure that delta T.
Right. Okay.
Yep. And yeah, and therefore it is the proper frame. That's another way to think about it. The proper frame is the one in which you only need a single clock or a single rod to measure whatever it is you're doing. Or a single rod, single clock, if that delta X equals 0, or a single point in time if delta T equals 0, a single stake, a single location. Maybe that's not the right way to think about it. Let me think about that.
No, that makes sense.
Okay, cool. Awesome. Any other questions? This is some weird stuff.
Yeah. Why do you need two clocks to measure it on the ground?
Because those two events happen at different locations, right? And so you need a clock at the first location and you need a clock at the second location. And even if you agree on what those clocks say, the train observer does not agree that those, let's say I agree on the ground that those two clocks are the same. The person on the train does not agree that those two clocks, says that those two clocks times do not agree with one another. Anything that happens at two different locations requires two different clocks.
Okay.
Okay, let's do I'm going to give you a quick problem solving guide. Might be helpful for some problems on this week's homework set. So, problem solving guide. Hint, carry out a problem in one frame and then relate to another. The hard part about all of this is switching reference frames. Do as much as you can in a single reference frame before you have to do either do it at the beginning and then, in other words, minimize the number of frame changes you have to do and make those frame changes as simple as possible. So carry out problem in one reference frame. Then relate to another. And in general, we'll follow a pattern with all of these problems. Identify the events you are measuring. If you can plot them on a Minkowski diagram, do so. It will help you visualize what's happening. Determine the proper frame. Where delta x equals 0 or delta t equals 0. So delta t, so for, let's say, for delta, if you have delta t equals 0, we call this a space-like event. You have some delta x, you can contract or uncontract to calculate a delta x prime. Delta t prime will not equal 0. Contract, uncontract. For delta x equals 0, this is a time-like, these are time-like events. You start with a delta t and a delta x equals 0, and then you can time dilate and undilate to figure out what delta t prime is in some other frame, and delta x prime in that other frame will not equal 0. Awesome. I've got 1 minute left, which is not really enough time to get into the example that I want to do. But let me just set that example up. This example was going to be, how fast must you be going to see lengths contracted by 1%? Okay, we'll actually do that example and do the math and figure out how fast you have to be going. On Wednesday, a reminder that I have normal office hours by Zoom only, of course, on Wednesday morning from 9:30 to 11:30 and Thursday morning from 9:30 to 11:30. We'll have class again on Wednesday, homework due Thursday, and I'll see you on Wednesday afternoon. Enjoy the rest of your Monday. You're welcome.
Bye-bye.
Bye.
Have a good day.
Bye.